Thank you, Professor Carroll, for the exciting talk and for taking us through the fascinating science and application of aerogels. So as you might see, we have a lot of questions coming in from the audience, and let me straight away start taking up questions. The first question, Professor Carroll, is from a participant uh, who is asking that if the density of aerogel is less than the density of air, will the material float in water? Float in air, sorry.
Well, that's we have the ones we work with are not lower than that. I know that some of the carbon ones are extremely light, and I've seen them photographed on top of a wheat stalk or a dandelion or something like that. I haven't seen any pictures of floating aerogels.
Thank you, Professor Carroll. The next question, Professor Carroll, is on the cost effectiveness of the process and the material that you have shown. So what are the major bottlenecks associated with large-scale production and applicability of the material? And does it compare with traditional materials used for similar applications?
Yeah, so that's an excellent question. And of course, when you're doing something at a laboratory scale, it's always more expensive than a scaled up process, because you're not able to purchase, for example, the chemicals at a bulk discounted rate. And so clearly adding something into, an established window integrated glass unit production facility, adding something is going to add some cost. The question is it an acceptable cost to the end user? And the same is true if you're talking about an insulating plaster or an insulating, flooring product. So the question is, how much is the energy savings? At what point is the energy savings going to pay for the change? And so you have to have a target amount. So I know that some of the work in terms of insulating materials that are not transparent, a lot of people are working on trying to use waste product sources of silicates, for example, because that is a much less expensive way to go about it than starting with the alkoxides. But again, when you start to do something in bulk, when you scale up, it does reduce the overall cost. And by making a process efficient, you can bring it down into the range where it would be an acceptable cost benefit. The product is slightly more expensive than a regular window, but it's going to give you energy savings, which are not only good for the planet, but are also good for your wallet. But the real thing is, how much does it cost to do the process? What do the chemicals cost? What is the cost of electricity? We've done a life cycle analysis of our RSCE process in conjunction with Professor Desiree Plata, who's actually one of our former students and is currently on the faculty at MIT. This was done while she was at Yale. They were looking at aerogels for oil spill cleanup applications, but we are about to do a life cycle analysis related to our window application in conjunction with Professor Barati from Perugia.
Thank you, Professor Carroll. I guess we had a question on life cycle analysis. So thank you for sharing insights on that. The next question, Professor Carroll, is from a participant who is interested in the fabrication process. So if you can comment a bit more on the optimized process parameters, the maximum minimum temperature requirements, time, pressure, and things like that.
Yeah, so it depends on what is in the pores, right? So it depends on whether you have a mixture of methanol and water, or you have a mixture of ethanol and water, or if you've done some exchanges and so you just have the alcohol, for example. But the critical point temperatures and pressures for the smaller alcohols are all similar to each other. The pressure, I don't have the number off the top of my head. The pressure is not that different from the CO2 pressure. It's the temperature that's a big difference. And so to take any of the alcohols supercritical, you need temperatures in the range of 260, 280 degrees C, and that is hot. And so some methods of making aerogels, I spoke mostly about silica aerogels. There's a lot of work being done with carbohydrate-based aerogels. aerogels based on cellulose types of materials. Our process is not suitable for those because of the temperature we have to go to. I also spoke mostly about our work with monolithic aerogels, but our method can also be applied to materials that have been gelled in advance. An advantage of our method for the monoliths is we don't have to do the solvent exchanges. But for some of the work in catalytic materials where the monolithicity is not required, we have done solvent exchanges, and that allows us to, instead of extracting a ethanol water mixture, we can just do the alcohol. We can do it at somewhat lower temperature as a result, because the critical point for water is really quite high. And so it's a little bit of a vague answer because it depends on what the chemical species are. The hydraulic hot press we're using is a standard hydraulic hot press. I should say the one that we're using in the laboratory. The company is building its own equipment to make aerogels, but the laboratory scale hot press that we've used is a 30-ton hot press. Hot presses come in various sizes, and so the amount of restraining force that you have over what area determines how large a monolith you can make. And so we're limited to about 100 by 100 millimeters. Is that right? Yes, about that size. But it's based on the hot press size, not the concept. That's
all right. Thank you, Professor Carroll. The next question is about waste material precursor for developing aerogels.
yes.
So what is the impact of functional groups, or do functional groups play a role in the fabrication of aerogels? Because usually it might be condensation reactions with functional groups. So if functional
Yes.
groups are not present in the waste material, or if it is present, does it have a role to play?
Yeah, so it depends what the source of the waste material is, right? And to what extent you would have to do a series of purifications first. In terms of the silica aerogels, there's such a variety of precursors that can be used, and some of them have additional functionality. There's advantages to making things hydrophobic, for example, because if an aerogel is hydrophilic and it comes in contact with water, it will cause the pores to collapse. And so for longevity of materials, a lot of the commercial aerogels are somewhat hydrophobic, and that can be done either by using a precursor that contains one or more branches that do not have the alkoxide and therefore have some organic functionality, or by surface modifying the material at the end of the process. So there are a wide variety of chemistries that can be employed, and it's a really exciting area. It's one of the things that's been very fun for me about engaging in this work, which has brought me quite a distance from the type of research that I initially did and that I did in my graduate and postdoctoral studies in the first 10 years of my faculty appointment, is that there's so many different applications and different ways of doing it. We'd really like to be able to do some of the cellulose work, but it's not going to work with our method. So there's some really exciting work going on in that area.
Thank you, Professor Carroll. The next question is on silica aerogels. So how do you control the monolithicity and shrinkage during the drying solvent removal process?
Yeah, and this is something that in our first few papers that we published, we got pushback from reviewers. Our method has essentially no shrinkage. The gel forms in the mold. We don't allow it to do any substantial aging. It doesn't pull away from the walls of the mold. And so it can actually be somewhat difficult to get the aerogels out of the mold. One of our things that we do, and I'm going to swing back several slides to show a picture of the mold approach. As you can see, this mold doesn't have a bottom. And so if we really want to make very monolithic aerogels, what we do is we initially use gasket material to seal the bottom of the mold. We pour things in, so we do an initial sealing. Hot presses can be used, for example, to laminate things. So this is something that's relatively easy to do. We push down so that this bottom part is then sealed. We pour the liquid precursors in, put fresh gasket material, and then do the process. When it comes out, we can then push the aerogel through. We have also experimented with some other designs, but if we really want to get monolithic aerogels out of our molds, we have to be able to do that. Otherwise, there is no shrinkage. This can be seen in our Journal of Visualized Experiments. It's a video article. It can also be seen in a very long video that is on the web that Dr. Steven Steiner from Aerogel Technologies did a sort of a podcast. It's not really a podcast, it's really a video. They came to the lab and they interviewed us, and they show the whole process, and you can see essentially the lack of shrinkage. And it's an advantage, and it also is a little bit of a challenge of the process. We've got to be able to get them out without breaking them. So unlike, say, an ice cube tray, right? You know that they don't come out very easily, because if you have an ice cube tray, sometimes you have to twist or something to get them out because there's no shrinkage. That's the situation that we're in with our materials.
Thanks, Professor Carroll. So I'll just take up a few questions on the applications of aerogels. Where the participant has asked, since aerogels are nanoporous materials and have insulation properties, what would be your take on using them for CO2 reduction application, for example?
Oh, yeah, there are groups that are looking at CO2 capture and those sorts of areas. That's not an area we've worked in, but there is definitely work being done in that area.
And did you also work on drug delivery applications with silica-based aerogels?
So there's been a lot of interesting work has come out of work that Irina Smirnova, who's at Hamburg, has done some work with that. I have had a couple of students that have done short-term projects with drug delivery that we haven't published in that area. One reason is that we're working with the silica aerogels, and there's been some work done in that, but biodegradable aerogels are a more attractive potential substrate for that. There has definitely been work in the literature for use of aerogels for drug delivery, and as I said, we've had a couple of students do some experiments with that. We are able to entrap, for example, ibuprofen in aerogels using our process. In fact, the ibuprofen is basic, so we could actually use it as the catalyst for the sol-gel reaction, and then we entrapped ibuprofen, and student was able to show that we could get at least some of the ibuprofen back out of the aerogel subsequently. But it has been sort of a side project for us. Working with the undergraduate students, sometimes we have the students working on something that's advancing our overall research efforts. Sometimes we have a student that comes to us and just says, can I use aerogels to, and they say something. And so we have had students that do what I call one-off projects. Sometimes those have led to really interesting long-term fundamental projects in the group. But it's nice to work with younger students. They're very enthusiastic, and they think anything is possible.
Thank you, Professor Carroll, for sharing the insights on that. So a couple of last questions, I would say. I'll take up one question on the sustainable building application, where the participant asked about the longevity of monolithic aerogel-derived windows compared to current products available in the market.
Yeah, we've and longevity, and also do the optical properties change? So we have, in conjunction with the group at Perugia, we've been doing a long-term study. We have with accelerated aging, exposure to simulated sunlight and humidity, equivalent to aging. We published a paper on the methods we were using, and we published sort of a midpoint paper when it had accelerated aging was 12 years. We've seen some slight changes in what's known as the color rendering, so the appearance through the window of different things in terms of, if you're looking through a window at a blue object as opposed to a yellow object or a green object, how is the ability of this window to be letting you see the object without distortion of the color. And we've also been looking at whether changes in hydrophobicity occur over time. So we've just finished that. We haven't published the last part of it, but we did essentially 20 years of artificial aging. We do see some changes, but a window lifetime is thought to be, on the order of tens of years. So 20 years seemed a reasonable time. The materials remain monolithic. That isn't the issue. It's just a question of whether some of their physical properties change.
Thank you, Professor Carroll. I'm aware that we are beyond time, but if it is okay, can we take up one last question? So you have commercialized the aerosol technology developed at Union. So if you could share some experience on taking things from lab to the market for budding early career researchers here, that would be really good. And you can just give a message to the audience to that.
Okay. I will say that is something I never thought I would do. And it's been really interesting to do it. The idea of taking something from the lab to the marketplace. I mean, we all want our research to matter, right? We all want to make an overall difference. And one way to do that is by translating the fundamental work you're doing that has these applications to the marketplace. But there are ways you don't have to do that from scratch. There are opportunities to learn about the process. So for example, the ACS has a small chemical businesses division. It's one of our technical divisions, and they have programming related to things like intellectual property and starting a business. In the US, the National Science Foundation also has a program that we participated in that's called Innovation Core, or I-Core, that teaches academic researchers about how do you commercialize something, or how do you know somebody wants to commercialize this? Just because it's very exciting doesn't mean everybody wants to use it, right? What is there actually a market for this? And doing customer discovery. And actually, my collaborators and I have a grant now from the National Science Foundation to support a series of workshops for other faculty from undergraduate institutions to think about entrepreneurship and technology transfer. And actually next Friday at this time, I'm going to be helping run a workshop at which we have people coming from 10 other and two internal groups coming in to learn more about that process. But there are resources available within ACS and other ways. But it's really, really rewarding to see work that you're doing potentially having an impact. And I think that's something we all want to do. So I really thank everyone for joining us today. I've really enjoyed this, and I look forward to interacting with people on LinkedIn and other ways. Thank you.